So how do we know if something's a function or not? What test does it pass? Vertical line test, right? So all the rules that we've been using so far are assuming that the thing is a function, that it's f of something or g of something, that it's going to be a function, and then it passed the vertical line test already. So what do we do if it doesn't? Right? What if a curve fails the VLT? Is it still possible to find the derivative? And the answer is yes, of course. Yes, it's still possible. But we need some special rules on how to do that. And so this is called implicit differentiation. So for example, let's start with 2x to the third minus 3y squared equals 8. So this is a relation. It is graphable, but its graph does not pass the vertical line test. And so how would we find the derivative of this function? All right, well, we're still going to take some of our same power rules that we had before, but then there's this additional chain rule that we need to use. And so the derivative of 2x to the third is 6x to the second, and then dx dx. We do that to indicate the chain rule and to show that this function does not pass the vertical line test. So the variables have the extra differential. We call that a differential on there. And then minus. So the 3y squared would be 6y, but it also would have dy dx. So every variable has its differential on it with respect to x. X is the axis that we're doing everything relative to, so it's not just because one of them's dx dx doesn't mean the other one's dy dy. It's always dx regardless of what the variable is. And then the derivative of 8, of course, is 0 because it's a constant. So this dx dx does reduce to 1, and then we need to get dy dx by itself. So we're looking at 6x squared minus 6y times dy dx equals 0. So we can kick the 6x squared to the other side. And so we'll have negative 6x squared. And then we'll divide. So dy dx is negative 6x squared divided by 6y, which reduces to negative x squared over y. So you'll notice that the derivative of something that fails the vertical line test has both x's and y's in it. Okay, so there's a negative here, and a negative there, and a negative there. All right, so now we're looking at positive x squared over y. Thanks, two negatives make a positive. So the derivative of an implicit, or the implicit derivative of a graph that does not pass the vertical line test is going to be implicit, which means it's going to have be based on x's and y's, not just x's anymore. So it's based on multiple variables.
So would there be two different derivatives at the same x?
Yes. Yes, because this function does not pass the vertical line test. So suppose it was like this, and I said, find me the slope at 2. Well, this 2 or that 2, right? One of them is going to have a negative slope, and one of them is going to have a positive slope, even though they share the same x. So this thing fails the vertical line test, so it's going to have two y's. It's also going to have two derivative values depending on which y you're at. That's why we call these, that's why the derivative is based on x. You have to know the x and you have to know the y in order to know what the slope is. Let's try another one. Okay. For the function x squared minus xy plus y squared equals 7, find the tangent line at the point -1, 2. So as Tom pointed out, you no longer can just say find the tangent line at x, because this function fails the vertical line test, and so this function will have an x paired with two different y's. So you have to know the x and the y to be able to find the slope. So when we take the derivative of this, we're going to have 2x dx dx minus, and now Trung, here's an example of having minus xy. And so it's not just going to be minus dx dx dy dx. That's not how that's going to work. Products are not just a simple product of the derivatives. So instead, we need to be able to apply the product rule in parentheses so that they're affected by the negative sign. So we will have y times dx dx. So y times the derivative of x plus x times the derivative of y. Then, for the y squared, it would be 2y dy dx as well, and then equals 0. So when we clean this up, we can simplify the dx's, but we have to remember to distribute the y, the negative. And so we'll have 2x distributed to a negative y and distributed to an x dy dx plus 2y dy dx. Dy dx equals 0. So we have multiple dy dx's in the same equation. So this is going to need some factoring. So we'll have negative x plus 2y. Both are dy dx, so that's factored out. And then negative 2x and positive y are on the other side. So we've moved the terms that don't have dy dx to the opposite side, and then we factored out the dy dx from the common term. So I did two things at the same time. And then we'll simplify. So we'll have negative 2x plus y divided by the quantity negative 1x plus 2y. That's not reducible. Those x's don't reduce, those negatives don't reduce, the y's don't reduce. That's in its final form. But since we know both x and y from the original equation, the original problem, we can substitute negative 2 for x, or negative 1 for x and positive 2 for y. So we'll have negative 2 times negative 1 plus 2 over negative parentheses negative 1 plus 2 times 2. So that will simplify for us, and we'll end up with 2 plus 2 as our numerator, and we'll end up with 1 plus 4 as our denominator, so we end up with a slope of 4/5. So at that particular point on the curve that's not a function, you still have the slope of 4/5. So the tangent line would be written in point slope form. So the tangent line would be y minus the y value of 2, the slope value of 4/5, and x minus the negative value of 1, so x plus 1. So that would be our tangent line. Okay, any questions about that one? Okay, finding the second derivative is my favorite. I like these. I find they're just a good challenge. So what if you need to find the second derivative? So find the second derivative. So we write it like that, d2y over the second, like that. So the 2 comes between the d and the y, but it comes after the x. The reason for that is it came from the way Leibniz used to write it. He would write it like this, the second derivative of y, and he would put y after, but eventually y sort of slid into the numerator, and people started writing it more like that. So that's why the 2 comes after the d but before the y. Just a little history. All right, so find the second derivative of the following function. 2y equals x squared plus sine y. All right, so we're going to find the second derivative of that. Now we've got y in multiple places, so clearly this thing is going to fail the vertical line test, so we need to be able to find the derivative. The derivative of 2y is the constant 2 times dy dx The derivative of x squared is 2x times dx dx. And now be careful about how you take the derivative of sine y. The derivative of sine y is the derivative of the outside, which is cosine, while leaving the inside alone. And then the chain rule would have you take the derivative on at the end. So when we clean this up, we've got a dx dx that simplifies, and I'm going to pull all the dy dx's to the left-hand side. So I've got 2 dy dx minus cosine y dy dx just being equal to the simple equation of 2x. So I simplified the dx dx, and I moved the cosine to the other side, which allows me to factor. And I'll have 2 minus cos y being equal to 2x. So my first derivative is 2x over 2 minus cos y. Now that's the first derivative. How do I find the second derivative of that? Quotient rule. All right, so the second derivative of that is going to be d2, the second derivative of what we just found, will be the quotient rule, which remember is ba prime minus ab prime all over b squared. So I'm going to take the base, which is 2 minus cos y, times a prime, which is 2 dx dx, minus a, which is 2x, times the derivative of the denominator, which is sine y dy dx, all over the base of 2 minus cos y quantity squared. Now this is my favorite part. What do I replace dx dx with? What do I replace dx dx with? No. What do I dx dx? What do I replace? Okay, that's with 1. What do I replace dy dx with? The derivative that we just had before. So I'm going to replace that. So to simplify this, we will have 4 minus 2 cos y. So I just distributed the 2 minus 2x sine y, and then replacing that derivative, we now have 2x over 2 minus cos y. And that whole thing is over 2 minus cos y quantity squared. So there's a lot of, you could continue to simplify this by getting a common denominator. There's lots more that you could do, but you don't have to. You could leave it like that. If you wanted to get a common denominator, you could. But I would say just leave it. Personally, I would say just leave it like that.